Okay, so this is going to be in section 4.6 in the book, and there are a couple initial little pieces that I want to cover before I get to the big piece. And the first thing is the fundamental theorem of algebra, and I'm just going to kind of summarize it versus what the book says. What this fundamental theorem of algebra is basically telling us is that whatever the degree of my polynomial is, in this case it's a cubic, that I'm going to have a total of 3 zeros. Now, I may not see all of those. It may not cross the x-axis 3 times. I may have something that looks like this, where I'm going to get 1 0 and 2 imaginary, but they're going to still add up to 3. You know, or I could have a situation where I have a touch. I'll have 2 zeros there and 1 0 there, so that's a repeated 0. But still, I'm going to add up to 3. They just may not all be that visible. So for this B, I will have 4 total zeros. For the next example, I would have 4 total zeros, either repeated or imaginary, or they could cross the x-axis. It could cross the x-axis 4 times, like that, or I may not see any. It may look like this. And I would have 4 complex zeros. Okay, looking at the next one down, I would have 3 zeros. Okay? All right, so moving to the next thing, imaginary solutions. One thing that I was going to clue me in that I'm going to have imaginary zeros is going to be when I have one of these. This is going to, we're going to learn this in a few days. Like this point here, that's a local minimum. And notice the way if it was longer, it would actually come down and cross the x-axis. But it's not. It's staying up above the x-axis. That would be an indication that I am creating a couple imaginary zeros. Just like when I drew this quartic over here, you can see that those 2 blips don't touch the x-axis. They would be creating imaginary zeros. So that's kind of graphically how you could tell that that's going to happen. Okay, let's go down to the last piece, and this is called Descartes' rules of signs. And here I just have another little diagram here. It says that, okay, these would both be generating what would be imaginary zeros there. So I would know that I would have 4 imaginary zeros for that quartic. That's a quartic. It's an x to the 4th. And so there would be 4 imaginary zeros. Now let's go down to the rule of signs here and see what this has to say. There may be a time when I want to know how many positive real zeros. Now that's a real zero that just has a positive number on it. Or a negative real zero, that would be still a real zero. You'd still cross the x-axis, that would have a negative on it. And what this guy did is he came up with a way to do that. And let's go over that. It says for the number, to find the potential number of positive real zeros, I'm going to take a look at the coefficients when the equation is written in the standard form and count up the number of sign changes that I have. And the number of real positive zeros will be that number of sign changes, or less than that by an even number. When it says less than that by an even number, it says just keep subtracting 2. Right? So, for example, if I had 5 sign changes, the number of positive real zeros I could have could be 5, or maybe it's 3, or maybe it's 1. If the number of sign changes I had is 4, the number of real positive zeros I would have could be 4, 2, or 0. That's what that less than by an even number means. Now, to find the number of negative real zeros, what I do is I actually put a negative on all my x values. Then I figure out how many sign changes there are going to be doing that. That tells me the number of negative real zeros. And it's the same thing. That's the maximum number they could be, or it could be less than that by any even number. So, for example, if I had 5 sign changes when I put in a negative x, What that means is I could have 5 negative real zeros. I could have 3 negative real zeros. I could have 1 negative real zero. So let's see how this works. And like I said, this isn't going to be a huge part of any test, but it's a good thing to know. You'll have to do it in pre-calculus and calculus. So here's an example out of the book, and we'll work another one after this, is I have an x to the 6th. Here's my original equation right up here. And let's try to find the number of positive real zeros. So that means I'm not making any change to the equation. This is exactly as written. I'm looking at the coefficient that's in front of x cubed. That's a positive number. Oh, look, it became negative. There's a sign change. Now this negative 2 went to a positive over here. That's another sign change. This positive 3 went to negative 10. Oh, that's another sign change. Now I have a negative to negative, no. Negative to negative, no. Negative to negative, no. So what I had is I had 3 sign changes. So that means the number of positive real zeros I could have could be a 3 or 1. Okay, now what we're going to do is we're going to find out the number of possible negative real zeros. So I simply take that x value and I put a negative on it, and then I calculate out what my new polynomial would be. Now, this is a little tricky, but it's not real hard. If I had a negative now on that x and it's raised to the 6th power, that's still going to give me, that would make a positive on the x, correct? Because it's a negative to the 6th. And the sign that's out in front of there is a positive right now. And so negative to the 6th is positive. Hey, that's going to stay a positive. Let's go to the next one. I have a negative on this x. It's to the 5th power. That's going to be a negative. Subtract the negative was going to make that this number is going to have to be 2x to the 5th, positive. Let's go to the next one. I have a negative to the 4th power. That's going to be a positive. There's a positive out here, so I have a positive and a positive. That would have to be a plus 3x to the 4th. Move to the next term. I have a negative and it's cubed, so cubing a negative is a negative. There's a negative out here. That's going to give me a positive 10x, so there's a positive. The next one, I have a negative. It's squared, so that'll be a positive. There's a negative out in front of it, so that's going to be a negative 6x squared. Moving to the next one, I have a negative x, a negative on the 8. That would come out to be a positive, so positive 8x minus 8. So finally, I have changed my equation to when I put the negative on the x, and I can count the number of sign changes. So positive to positive, that's a no. Positive to positive, no. Positive to positive, no. Positive to negative. Wait a second, I missed. Yeah, I'm right here. So I've got a positive going to this negative. Yeah, that's a sign change. Now the negative flips back to positive right here. Yeah, that's a sign change. The positive going to the negative over here. Yeah, that's a sign change. So I have 3 sign changes when I put the negative on the x. So what that could mean is I could have 3 negative real zeros, or I could have 1 negative real zero. Okay, so now I figured that out. And so what I'm going to do is I'm going to make a little chart. And it doesn't matter what order you put the chart in, but I know that I have 3 R1 positive real zeros. And I could have 3 R1 negative real zeros. So I just have to include every combination of that. So that's what this chart says. Okay, I could have 3 positive or 3 negative, 3 positive, 1 negative, 1 positive, 3 negative. That's just all the combinations of those possibilities. And I know that my number of total zeros, because this was an x to the 6th. So the total number of zeros I have has to be equal to 6 in all cases. So by adding these together, I can figure out the number of imaginary zeros. So if it was the case where I had 3 positive, 3 negative, I couldn't have any negative real zeros. If I had 3 positive and 1 negative, I'd have 2 negative zeros. 1 positive, 3 negative, and I'd have so on and so forth. Do you see how that table's made? Okay. So let's try maybe one more. Okay, so let's do the next one. Here is the polynomial, and what I'm going to do is just as it's written for the number of even for the number of positive real roots, I'm simply going to count the number of sign changes. Now, this is a plus out here, so there's one sign change. Negative to negative is no. This negative to this positive is a sign change. This positive to the positive here is not. Positive to positive is not. This positive to this negative is. So the potential number of positive real roots, or I have 3 sign changes, are less than that by an even number. I could have 3 or 1. Okay, now let's do the negative part of that. So what I would do is I'm going to put a negative x into all of those. So I would have 2 times a negative x to the 6th minus 5 times a negative x to the 5th minus 3 times a negative x to the 4th plus 3 times a negative x cubed plus 10 times a negative x squared plus a negative x minus 9. So let's go ahead and simplify that. This would be a negative to the 6th. That's going to be a positive number, so I'm going to have plus 2x to the 6th. Now I have a negative to the 5th. That's a negative number, but it's subtracted in the front out here by the 5. That would be plus 5x to the 5th. A negative to the 4th is going to be a positive number, but there's a negative in front of the x, so that on the front of the 3, so that would be minus x to the 4th. A negative cubed is negative. The sign in front of the 3 is positive, so that would make that a negative 3x cubed. Negative squared is positive. It's a positive in front of there, so I got plus 10x squared. Negative x would make that a minus x minus 9. So the number of sign changes. No in the front. Here's 1. No sign change there. This is a sign change, and this is a sign change. So for my negative reals, I have 3 sign changes, or 2 less than that could be 3 or 1. So I'm going to make my little chart, and I said that I could have 3 positives, or I could have 1 positive, and then the combination with the negatives could be 3, 1, 3, 1, right? So I've covered all my combinations of a potential 3 positive and 3 negative, and they have to total up to 6, each one of those. And so if I had 3 positives and 3 negatives, I wouldn't have any imaginary. 3 positives and 1 negative, I'd have 2 imaginaries. 1 positive and 3 negatives, I would still have to have 2 imaginaries. And if I had 1 positive, 1 negative, I'd have to add up to be 6. Those would give me 4. I'd have to have 4 imaginary roots.